On November 15, 1942, the Imperial Japanese Navy battleship Kirishima steamed confidently through the darkness south of Savo Island. Her crew, relying on superior night optics and intensive training that had given Japanese gunners a decisive edge in previous engagements. Captain Sanji Iwabuchi peered through advanced optical rangefinders, unaware that 8,400 yards away, the USS Washington had been tracking his every move for 7 minutes using revolutionary radar technology that could see through darkness, smoke, and rain. At precisely 100 hours, Washington opened fire with her 16-inch guns, launching shells that screamed across the black waters to strike Kirishima with devastating accuracy. Historical accounts based on Japanese damage reports suggest between 9 and 20 direct hits within the first minutes of engagement. Within 7 minutes, Kirishima's steering jammed, her main battery fell silent, massive flooding threatened to capsize her, and flames consumed her superstructure. By 3:25 hours, the battleship rolled over and sank, taking 212 crew members with her while 1,098 survivors were rescued. Captain Iwabuchi survived, genuinely believing his guns had scored hits on the American battleship, unaware that every Japanese salvo had missed its mark because Washington had never entered visual range, instead appearing out of nowhere, firing with impossible accuracy, and vanishing back into darkness completely untouched. This was not luck, but the result of radar-directed fire control operating against an enemy who couldn't see their attacker, with Washington's Mark 8 radar tracking Kirishima continuously, while Mark 1A computers calculated firing solutions faster and more accurately than any human crew could achieve. Japanese naval doctrine, built on decades of experience, held that night battle belonged to the side with superior optics and better-trained lookouts. By every 1941 measure, the Imperial Japanese Navy possessed both. Yet at Guadalcanal something fundamental had shifted as Americans changed naval warfare's rules, while Japanese commanders struggled to comprehend the technological superiority, so vast it seemed incomprehensible. Japanese confidence in naval superiority had deep roots extending to the Russo-Japanese War of 1904–1905, cultivating excellence through rigorous training, tactical innovation, and technological advancement. Officers spent years mastering night combat, visual gunnery, and torpedo tactics, while enlisted men trained relentlessly in optical recognition, range estimation, and rapid gun laying, producing lookouts who could identify ship silhouettes at greater distances than American counterparts and gun crews, achieving accurate fire faster after target acquisition. The Type 93 Long Lance torpedo exemplified Japanese naval philosophy, taking existing technology and perfecting it through meticulous engineering, before deploying with crews trained to exploit every advantage. This oxygen-powered weapon could strike targets at 44,000 yards while traveling 38 knots without telltale wake, carrying a 490-kilogram warhead that doubled American torpedoes' punch. In engagement after engagement during the war's first year, this philosophy produced victories like Savo Island in August 1942, where Japanese cruisers devastated an Allied force, sinking 4 heavy cruisers in less than an hour through superior training and tactics. Meanwhile, Americans fought a different kind of war where Japanese development focused on perfecting existing capabilities, while American development aimed at changing naval combat's fundamental nature, a difference invisible to Japanese observers until too late. American naval radar development began not with military requirements but scientific curiosity, as 1930s Naval Research Laboratory physicists studied radio wave propagation, discovering ships reflected detectable radio wave patterns. This laboratory curiosity transformed into deployable military capability through systematic American approach, with USS New York conducting the first successful radar-directed gunfire test in 1940. Though crude, requiring multiple operators and manual calculation, The system worked. Guns could aim at targets beyond visual range, catching Admiral Ernest King's attention as Commander-in-Chief of the U.S. fleet. King recognized radar represented not incremental improvement but complete transformation, pushing for rapid development and integration into every naval operation. Detection, tracking, fire control, navigation, and aircraft direction. The challenges were staggering. 1940 radar technology was experimental, requiring reliability for combat deployment, compactness for shipboard installation, and precision exceeding pre-war industrial standards. Americans solved these problems through systematic industrial organization rather than individual genius, establishing the Massachusetts Institute of Technology Radiation Laboratory in October 1940, employing over 4,000 scientists and engineers within a year to develop more than 100 different radar systems, optimized for specific tactical applications throughout the war. The Radiation Laboratory represented American organizational genius applied to technological warfare, with university scientists converging on Cambridge campuses to focus theoretical knowledge on practical applications. Operating principles seemed chaotic to traditional military research, but produced remarkable speed through parallel research teams working on overlapping problems, encouraged competition, immediate solution sharing, and rapid failure analysis distribution. This innovation ecosystem accelerated progress across adjacent fields, producing Mark V radar for aircraft tracking, Mark 8 for surface fire control, Mark 12 for improved surface tracking, and Mark 22 for close-range anti-aircraft work, each addressing tactical needs identified through fleet feedback, with engineering teams modifying designs within weeks when combat reports revealed limitations. Manufacturing integration was built into research from the start, with laboratory engineers working directly with industrial partners to ensure mass-producible designs, testing prototypes for manufacturability, and standardizing components across multiple systems to simplify production and maintenance. This approach meant laboratory developments reached fleet deployment faster than Japanese systems moved from prototype to initial production, while Japanese radar research remained primarily academic through 1943, with brilliant university scientists making genuine component advances, but lacking organizational structure to translate these into deployed fleet systems due to compartmentalized research, laboratory competition for limited resources, and failure to build the systematic bridge from laboratory to factory to fleet that Americans achieved. American industrial strength concentrated in this approach. Japan had brilliant scientists but lacked industrial depth to transform ideas into thousands of identical units deployed across entire fleets, with the difference lying in systematic application at scale rather than scientific capability. The Mark 8 fire control radar entering service in mid-1942 could track surface targets at 25,000 yards in complete darkness, providing sufficiently accurate range, bearing, and rate of change data to direct main battery guns. Though imperfect, with early versions suffering interference and false returns, American doctrine accepted imperfection if systems worked well enough for tactical advantage, while Japanese technology demanded perfection before deployment, delaying practical application despite 1939 development of a 10-centimeter cavity magnetron, representing significant achievement. By the time Japanese radar reached meaningful fleet deployment, American systems had advanced through multiple generations, widening gaps through dozens of parallel efforts feeding improvements back into the industrial base. Mark 8 limitations prompted Mark 12 development with improved discrimination. Mark 12 insufficiencies for anti-aircraft work drove Mark 22 optimization for aircraft tracking, with each iteration taking months, not years, and deploying across fleets as quickly as ships could be retrofitted. Japanese naval technology development couldn't match this pace with limited resources, stretched industrial capacity building ships, aircraft and weapons, and radar development, assigned to competing research groups with limited coordination, and no radiation laboratory equivalent pushing systematic improvement across all applications simultaneously. By mid-1943, American surface combatants routinely carried multiple optimized radar systems. SG surface search radar providing long-range detection, fire control radars guiding guns, and air search radars detecting incoming aircraft at distances allowing effective combat air patrol vectoring, all integrated through plotting rooms where operators synthesized electronic data into comprehensive battlefield awareness. Japanese ships in the same period typically carried single radar systems used primarily for early warning with minimal weapons integration, keeping fire control primarily optical and rendering them partially blind in night combat against clearly seeing enemies. The Guadalcanal demonstration of this disparity proved brutal through Rear Admiral Willis Augustus Lee Jr.'s command of Task Force 64, built around battleships Washington and South Dakota, with 4 destroyer screens, mission to prevent Japanese Guadalcanal reinforcement against Admiral Kondo's strong force, centered on battleship Kirishima with multiple cruisers. Lee's unique qualifications for radar-directed night action included 5 gold medals in shooting at the 1920 Antwerp Olympics, demonstrating precision and calculation defining his command style, plus involvement in radar development and testing, since earliest days providing understanding of capabilities and limitations that gave rare confidence in fighting based on electronic rather than visual information. Lee had conducted exercises using radar for fire control, seeing systems work in tests, and knowing they provided accurate firing solutions at ranges where optical systems were useless, making him willing to exploit capabilities other commanders might have been too cautious to trust in combat. Lee's force made contact at 23:17 hours on November 14, with SG radar detecting Japanese ships beyond 18,000 yards, holding fire while Japanese forces approached and fire control radars locked on to compute solutions, requiring discipline as crews heard Japanese forces through sound gear and lookouts strained for visual glimpses while Lee trusted radar to indicate when to fire. Japanese forces relying on visual detection remained unaware they had been detected and tracked, splitting to attempt flanking maneuvers tactically sound against optically detecting enemies, but futile against radar tracking, as Lee's plotting rooms maintained perfect awareness of Japanese dispositions. At 100 hours with Japanese ships at 8,400 yards still unaware of Washington's position, Lee ordered batteries released. Washington's main battery spoke first with 16-inch guns firing on radar solutions in complete darkness. The salvo hitting as Kirishima's superstructure erupted in flames, providing first visual confirmation to Japanese observers when it was already too late. Washington's fire control radars held lock, delivering salvo after salvo with mechanical precision, while Kirishima attempted return fire, her optical rangefinders struggling to acquire Washington through darkness, smoke, and rain squalls, with the few managed salvos being unguided estimates based on muzzle flashes that all missed their target. Within 7 minutes, Kirishima was mission killed, dead in the water with critical damage, sinking 3 hours later after Washington fired 75 16-inch shells scoring at least 9 direct hits, possibly 20, against Kirishima's handful of poorly aimed salvos, disparity stemming not from courage or training but fundamental capability as Lee fought with perfect information against Kondo's blindness. Kondo's after-action report noted American forces demonstrated seemingly impossible detection and fire control capabilities, with Japanese observers reporting American salvos arriving with uncanny accuracy, despite absent searchlight illumination or visible optical rangefinder use. Some officers speculating about new extraordinarily powerful optical systems, since radar use for blind fire targeting seemed beyond credibility. skepticism born not from stupidity but experience. As Japanese doctrine held radar lacked fire control precision, true for Japanese radar, but not American systems. With Japanese engineers having no way of knowing American technology had advanced so far beyond their assumptions, the truth about American radar superiority began penetrating Japanese thinking through accumulated evidence, with Lieutenant Commander Toshikazu Amori of the 8th Fleet tasked with analyzing patterns in American tactical success. Collecting after-action reports from multiple engagements revealed a consistent pattern. American forces consistently initiated fire at ranges exceeding visual detection capability, demonstrated night combat accuracy exceeding optical system explanations, and maneuvered with perfect awareness of Japanese positions regardless of visibility conditions. Amori concluded Americans possessed detection systems fundamentally superior to Japanese equipment, estimating American radar technology was approximately 2 years ahead of Japanese capabilities. His early 1943 report met skepticism from staff officers who found the assessment too pessimistic, psychologically struggling to accept that technology from a nation Japanese propaganda had dismissed as decadent and industrially weak could be 2 years ahead. Yet Amori was correct, and the gap kept widening. By mid-1943, the technological disparity had expanded to 3 years, with American destroyers commissioned in 1943 carrying radar suites more capable than those on Japanese battleships, while American fire control systems integrated with mechanical computers that automated firing solutions and removed human calculation delays. The Mark 37 gun director represented radar integration with mechanical computation, combining optical rangefinders with radar tracking to feed data into Mark 1A computers calculating firing solutions. This system could track targets visually when possible, switch seamlessly to radar tracking when targets were obscured, and maintain fire control solutions during transitions between modes. The Mark I fire control computer was a mechanical marvel, a room-sized assembly of gears, cams, and servo mechanisms continuously solving differential equations describing projectile ballistics. Operators input target data, ship motion, wind speed, and powder temperature, while the computer automatically calculated gun elevation and bearing, adjusting continuously as targets maneuvered. Earlier mechanical computers required human operators to input manual adjustments based on observed fall of shot, but Mark 1A integrated radar feedback directly into calculation loops. When radar showed projectiles falling short, the computer automatically adjusted elevation for the next salvo. This closed-loop fire control was revolutionary, removing human reaction time from the targeting cycle to produce sustained, accurate fire at ranges where visual systems couldn't function. American battleships could engage targets at 20,000 yards in darkness or poor visibility, while maintaining hit rates considered excellent in daylight action with optical systems, while Japanese battleships attempting return fire were reduced to firing at muzzle flashes with no ability to observe fall of shot or correct aim. Technical sophistication extended beyond individual systems to integration across ships through combat information centers that brought together radar data from multiple sources. Surface search radar providing overall battlefield picture, fire control radar tracking specific targets, and air search radar detecting aircraft. Operators synthesized this information into comprehensive awareness, distributed to all stations through interior communication systems, creating command advantages as significant as individual systems' technical advantages. American commanders fighting night actions had accurate real-time information about friendly and enemy positions, enabling maneuvers based on complete battlefield awareness, while Japanese commanders lacking equivalent integration made decisions based on fragmentary reports from lookouts who could only see nearby engagement portions. Japanese naval gunnery remained dependent on human calculation, with rangekeepers assisting computations but final firing solutions requiring trained operators making manual adjustments. Effective when visual contact allowed continuous observation, but nearly useless when targets existed only as radar returns. The technological gap manifested in every naval operations aspect, with American carrier task forces operating air search radar detecting incoming raids beyond 100 miles, allowing combat air patrol vectoring for intercepts before Japanese aircraft reached launch range for their own strikes, while Japanese carriers lacking equivalent capability relied on visual detection for combat air patrol, often learning of incoming raids only when American aircraft appeared overhead. The June 1944 Battle of the Philippine Sea demonstrated American radar superiority at fleet scale, with Vice Admiral Jisaburo Ozawa commanding 9 Japanese carriers with over 400 aircraft, planning to use superior aircraft range to strike American carriers while remaining outside American strike range. This plan required Japanese scouts locating American forces first and Japanese strikes avoiding American combat air patrol during approach. Neither assumption held as American radar detected Japanese scouts at extended ranges. When Ozawa launched his first 69 aircraft strike wave on June 19 at 8:30 hours, American radar detected the formation while still forming over Japanese carriers, and by 900 hours, American fighter directors had vectored Hellcats to intercept. The Japanese strike encountered coordinated defense, with fighters positioned by radar guidance for maximum intercept efficiency. Fighter directors aboard carriers watched radar screens showing friendly and enemy formations, vectoring combat air patrol to calculated intercept positions, maximizing defensive effectiveness, while Hellcat pilots received continuous radio updates on enemy position, altitude, and heading, approaching Japanese formations from optimal attack angles to achieve surprise despite daylight attacks. Japanese strike leaders found themselves intercepted before reaching attack positions, with formations broken by coordinated attacks from multiple directions, while surviving pilots faced anti-aircraft fire from ships alerted by radar with preparation time. Proximity-fused shells filled the air with fragments damaging aircraft even from near misses. Of the first wave's 69 aircraft, only 27 survived to return without scoring any American ship hits. Ozawa launched 3 more strikes that day, the second 129 aircraft wave launching at 9:56 hours and detected by American radar at 9:15 hours, with fighter directors scrambling additional combat air patrol and positioning forces for optimal intercept to shoot down 97 Japanese aircraft, while only 6 damaged American ships non-critically. The third 47 aircraft wave launching at 1,000 hours with 27 shot down, and the fourth 82 aircraft wave launching at 1,300 hours with 73 shot down. By day's end, Japan had lost 346 carrier aircraft against American combat losses of 29 aircraft. The numbers revealed systematic slaughter, with Japanese formations destroyed through industrial efficiency as each wave received identical treatment, radar detection at long range, fighter direction to optimal intercepts, coordinated attacks breaking formations, and radar-guided anti-aircraft fire. The system worked regardless of Japanese aircraft numbers or tactics employed. From Ozawa's perspective aboard carrier Teiho, the battle represented incomprehensible disaster, with strike after strike departing to attack American carriers, none achieving significant hits, few aircraft returning, and radio communications from strike leaders indicating attacks by fighters who seemed to know exactly where Japanese formations would be. The only explanation being American detection capabilities, exceeding anything Japanese intelligence believed possible. The psychological impact on surviving Japanese pilots proved profound, with Lieutenant Masatake Okumiya, a carrier division commander who later wrote extensively about Japanese naval aviation, noting in post-war writings that after the Philippine Sea, Japanese pilots increasingly felt they fought enemies who could see them coming from impossible distances. Not superstition, but accurate assessment of radar capability, creating tactical omniscience. American technological superiority extended beyond detection and fire control into weapons themselves through the proximity fuse developed at the Applied Physics Laboratory and Section T of the National Defense Research Committee, entering combat use in January 1943. This fuse used a miniature radar transmitter to detonate shells when passing near aircraft, dramatically increasing anti-aircraft fire lethality. The first combat use occurred on January 5, 1943, when cruiser Helena fired proximity-fused 5-inch shells against Japanese aircraft off Guadalcanal, with immediately apparent results as hit rates against maneuvering aircraft increased dramatically. Shells that would have been clean misses with contact fuses now detonated close enough to damage or destroy targets with fragments. Proximity fuse development represented American technical achievement at its finest, requiring devices to withstand gun-firing shocks exceeding 20,000 times gravity, operate reliably after extreme acceleration, vibration, and temperature changes, discriminate between aircraft targets and surface clutter like waves, function in rain, clouds, and varying humidity, and be cheap enough for mass production as expendable munitions. Solving these problems required advances across multiple fields. Vacuum tube miniaturization, creating radio transmitters small enough for shell casings. Battery technology surviving firing shock while providing power for few seconds of shell flight. Arming systems preventing premature detonation while activating fuses at safe distances from firing ships. And manufacturing processes producing millions of units with consistent reliability. The proximity fuse program involved over 4,000 people working across multiple laboratories and factories, with component production distributed to minimize security risks, final assembly in dedicated facilities, and quality control testing every unit before acceptance. The system produced over 100,000 proximity fuses monthly by 1944. Japanese air crews suddenly faced defensive fire exploding near their aircraft, with psychological impact amplified because Japanese intelligence didn't understand how fuses worked, and pilots couldn't develop countermeasures against unknown threats. Japanese engineers knew proximity fuses were theoretically possible, with multiple research groups studying the concept, but building them required industrial capacity, precision manufacturing, and systematic quality control at scales Japanese industry couldn't match while simultaneously producing ships, aircraft, and conventional weapons. The proximity fuse wasn't simply one invention, but the product of an entire industrial ecosystem optimized for high-technology mass production by late 1944. The technological disparity had become so severe that American and Japanese naval forces were essentially fighting different wars. American planning assumed comprehensive radar coverage, automated fire control, and integrated command through combat information centers, designing operations around these capabilities while considering night operations routine, since radar made darkness tactically irrelevant. Japanese planning assumed engagements would be decided by visual detection and manual gunnery, treating night operations as high-risk endeavors requiring specially trained forces, because capabilities remained primarily optical. This meant Japanese commanders faced constraints American commanders had eliminated through technology, as illustrated by the Battle of Surigao Strait on October 25, 1944, where Vice Admiral Shoji Nishimura led 2 battleships, 1 cruiser, and 4 destroyers through Surigao Strait in darkness to attack American landing forces at Leyte Gulf. Detected by American patrol craft at 2:36 hours. Radar tracked Nishimura's advance into a trap where Rear Admiral Jesse Oldendorf commanded American blocking forces, 6 battleships, 8 cruisers, and multiple destroyer squadrons, positioned for classic crossing-the-T tactics with radar guidance. American destroyers launched torpedo attacks guided by radar tracking, while battleships opened fire at approximately 20,000 yards with main batteries directed by radar fire control, destroying Nishimura's force in detail. Both battleships sunk, the cruiser sunk, 3 destroyers sunk, and the remaining destroyer fled damaged with minimal American casualties. The battle was less a fight than an execution, with Japanese forces advancing unknowingly into preset positions where radar-guided weapons achieved perfect surprise and devastating accuracy. Nishimura had sailed blind into enemies watching his every move, with Japanese lookouts never detecting American battleships until salvos began landing, their first indication of American presence being shells exploding among their ships as they attempted return fire, without clear targets against battleships remaining at ranges where visual detection was impossible in darkness. The engagement lasted less than 30 minutes, demonstrating that advancing through confined waters at night against radar-equipped opponents was suicide. Lieutenant Commander Amori's post-battle analysis noted Japanese forces had attempted tactics that would have been sound against opponents with similar technological limitations, but proved fatal against radar-equipped forces with fire control automation, a clear lesson arriving too late to affect Japanese operational planning. The full statistical picture of American industrial output became apparent only after war's end, with American shipyards producing 28 fleet carriers between December 1941 and September 1945, against Japan's 17 carriers of all types, most converted from other hulls rather than purpose-built. American production included 71 escort carriers, small carriers built on merchant hulls optimized for submarine warfare and amphibious support that provided distributed air power across the Pacific, while Japanese production included no equivalent since doctrine focused on fleet carriers for decisive battle rather than distributed air power for continuous operations. American shipyards produced 8 new Iowa or North Carolina-class battleships, incorporating radar and fire control technology from initial construction, with designs optimized for electronic system integration. North Carolina-class vessels authorized pre-war were retrofitted with improved radar during construction, while Iowa-class incorporated lessons learned from early combat with electrical systems and interior layouts designed around radar integration from keel up. Japanese battleships Yamato and Musashi represented traditional battleship design apex, 64,000 tons displacement, 18-inch main batteries throwing shells weighing over 1 ton, and armor designed to resist any existing battleship shells as engineering marvels and the largest battleships ever constructed. But they were built around obsolete assumptions, emphasizing visual range-finding with extraordinary quality optical equipment and fire control systems relying on trained operators manually computing solutions, while carrying radar as an afterthought retrofitted into spaces not designed for it. Poor integration produced limited capability. Against radar-equipped opponents, Yamato and Musashi's advantages in armor and armament were negated by inability to bring guns to bear effectively, illustrating diverging philosophies where Japanese design prioritized perfect execution of traditional naval warfare, while American design prioritized new technology integration that changed naval warfare's nature. Japanese battleships were built to win traditional gun duels, while American battleships were built to fight integrated actions where radar-guided guns engaged targets at ranges visual systems couldn't reach. The disparity extended through every category: 377 American destroyers against roughly 63 Japanese destroyers, with late-war American destroyers carrying radar suites providing detection, tracking, and fire control capabilities approaching pre-war cruisers, while Japanese destroyers remained primarily gun and torpedo platforms with limited electronic capability. 232 American submarines against 126 Japanese submarines saw American submarines equipped with radar allowing surface attacks at night with minimal detection risk, while Japanese submarines relied primarily on periscope observation, limiting effectiveness against alert opponents. American escort carriers, 71 vessels built on merchant hulls, provided distributed air power across the Pacific operating in amphibious landing support, anti-submarine patrols, and convoy air cover, while Japanese production included no equivalent vessels since doctrine remained focused on fleet carriers for decisive battle rather than distributed air power for sustained operations. The numerical disparity understated the real gap since Essex-class carriers commissioned in 1944 represented more combat power than 2 or 3 earlier Japanese carriers. In 1944, American destroyers could perform missions requiring 1941 cruisers. The compound effect of numerical and technological superiority meant American forces overmatched Japanese forces by widening margins as war progressed. Essex-class carriers, the late-war American carrier backbone, represented industrial power and technological advancement integration through standard 27,100-ton displacement, 33,900-ton full load, 872-foot length, and capacity for 83 108 aircraft depending on type mix. But numbers didn't capture what made them dominant. Each carried multiple radar systems providing comprehensive awareness through air search radar detecting aircraft beyond 100 miles, surface search radar tracking ships to the horizon, height-finding radar determining detected aircraft altitude, and fire control radar guiding anti-aircraft batteries. All integrated through combat information centers staffed by radar interpretation specialists, giving Essex-class carriers impossible battlefield awareness for earlier carriers. 24 Essex-class carriers were built, 32 ordered but 8 canceled after Japanese surrender, with 17 seeing World War II combat to provide striking power destroying Japanese naval aviation, supporting Pacific amphibious operations, and ultimately striking Japan itself. These carriers operated with aggressiveness that would have been reckless without technological advantage, regularly operating within Japanese land-based aircraft range because radar gave sufficient warning to coordinate defense. Combat air patrol could be maintained over task forces and guided to intercepts by fighter directors watching radar screens, allowing American carriers to operate in waters Japanese carriers avoided as too dangerous. Late-war Japanese carriers were reduced to operating from positions where land-based air cover could provide protection their own radar couldn't, reversing roles as Japanese forces sought cover, while American forces ranged freely. Confident technology gave decisive advantage regardless of enemy numerical strength in any area. The technological transformation proved so complete that by war's end, American naval forces operated with assumptions Japanese forces couldn't match. Night operations were routine for radar-equipped American ships, while Japanese forces still treated them as requiring special conditions and specially trained crews. American carriers operated offensively close to enemy bases, while Japanese carriers operated defensively under land-based air cover. American battleships hunted enemy warships, while Japanese battleships were relegated to secondary roles with main batteries largely irrelevant against enemies striking from ranges exceeding visual detection. The lessons Japanese officers drew from war would shape modern warfare understanding, with Lieutenant Masatake Okumiya, who survived to become Japan Air Self-Defense Force Lieutenant General, writing extensively about Japanese experiences. His post-war writings, including co-authoring Midway, The Battle That Doomed Japan with Mitsuo Fuchida, analyzed how technological inferiority had systematically undermined Japanese tactical advantages. Okumiya had graduated from the Imperial Japanese Navy Academy in 1930, serving as Carrier Division Commander during war with combat mission experience and operational planning perspective, combining tactical experience with strategic understanding to become important Japanese naval history interpreter for American audiences. His central thesis held that Japanese forces had entered war with tactics and training optimized for 1941's technological baseline, while American forces had systematically raised that baseline through continuous technological deployment. By 1943, Japanese tactical advantages in visual detection and manual gunnery became irrelevant since engagements were decided by radar and automated fire control. With Japanese forces fighting outdated methods against enemies who had changed combat's fundamental nature. Okumiya emphasized this wasn't Japanese courage or tactical skill failure. Pilots and sailors fought with determination throughout war, with unit cohesion and fighting spirit remaining high despite deteriorating material conditions. But spirit couldn't overcome systematic technological disadvantage, since the bravest pilot couldn't defeat radar-guided fighters intercepting his formation before reaching attack range. Lieutenant Commander Amori, whose wartime intelligence analysis had correctly identified American technological superiority early, was extensively interviewed by United States Strategic Bombing Survey after Japanese surrender, with survey interrogators describing him as Japan's most reliable and accurate information source as he provided detailed analysis of Japanese operations, strategic decisions, and American capability assessments. Amori had graduated from Imperial Japanese Navy Academy in 1922, serving as staff officer in various fleet commands, with access to operational intelligence and strategic planning. His analytical skills proved invaluable to American interrogators seeking Japanese decision-making understanding. His post-war writings for United States Naval Institute proceedings provided detailed Japanese perspective on technological gap. With his 1951 Japanese commentary on Guadalcanal, article offering insights correcting American understanding of several engagements, before serving as consultant to Admiral Samuel Eliot Morrison for multi-volume United States naval operations in World War II history. Amori's assessment concluded Japanese naval forces were defeated not through courage lack or poor tactics, but through systematic technological inferiority, making individual battles increasingly unwinnable as war progressed. He estimated American radar and fire control technology had been approximately 2 years ahead of Japanese equivalents in late 1941, widening to 3 years by mid-1943, and expanding to at least 5 years by war's end, since American industrial and research capacity allowed rapid iteration and improvement, while Japanese capacity was overwhelmed, simply trying to deploy earlier generation systems. American radar development progressed through multiple generations during the war, while Japanese radar development struggled to deploy first-generation systems widely. The compound effect of technological advancement meant initial advantages grew exponentially. Amori noted Japan's fundamental error wasn't failing to develop advanced technology, but failing to understand that modern industrial war required continuously advancing the technological baseline across the entire military structure. Individual brilliant systems proved meaningless without mass production, widespread deployment, and continuous upgrading capability. American victory stemmed from systematic technological deployment at scale rather than individual technical breakthroughs, an understanding arriving too late to affect the war's outcome. For American naval forces, the war validated a warfare approach that would define American military doctrine for decades. Technology could create advantages so decisive that traditional factors like individual courage, unit training, and tactical skill became secondary. Investing in technological superiority delivered returns exceeding any other military investment. Officers returning from the Pacific War carried the conviction that America must never allow technological gaps to develop against it. The radar and fire control systems that defeated Japan led directly to guided missiles, computerized battle management, and network-centric warfare, maintaining the constant philosophy of removing humans from decision loops where machines performed better, automating everything automatable, and integrating systems for synergistic effects exceeding individual capabilities some. The Japanese Navy of 1941 had been a formidable force built on decades of experience and training. Officers were professionals who had spent careers mastering their craft. Enlisted men were trained to standards exceeding most naval forces. Equipment was modern and well-maintained, and tactics were sophisticated and well-rehearsed. By conventional measures, the Imperial Japanese Navy ranked among history's finest naval forces. But conventional measures proved inadequate when combat's nature changed. Experience and training built for one technological era proved insufficient when the era shifted. The Americans hadn't simply defeated the Japanese Navy, they had made Japan's Navy type obsolete. The fast battleship, mass torpedo attack, and night engagement with superior optics, all elements Japanese doctrine emphasized, became secondary to the overwhelming advantage of seeing the enemy when the enemy couldn't see you. Battleship Kirishima had been modern and powerful by 1941 standards. Her optical rangefinders represented the finest available technology. Her crew had trained for years in visual gunnery and night combat techniques. None of this mattered when she faced an enemy tracking her through undetectable electronics, computing firing solutions through unmatchable machines, and striking with accuracy her optical systems couldn't achieve. In 7 minutes of radar-directed gunfire, USS Washington demonstrated technological superiority's decisive nature. The engagement wasn't close, not a battle between equals where courage or skill tipped the balance, but systematic destruction of an opponent lacking technology to fight back effectively. Kirishima's crew fought bravely. Her officers made tactically sound decisions based on available information, but they fought blind against an enemy seeing perfectly. This formed the essential lesson of American technological superiority. In the Pacific War, victory belonged not to the Navy with most courage or best training, but to the Navy successfully deploying advanced technology across the force. Individual heroism, tactical brilliance, and professional excellence remained important, but couldn't overcome systematic technological inferiority. The Americans had leaped ahead, with the gap widening throughout the war. Japanese forces fought with increasing desperation as they realized they were overmatched not just numerically, but fundamentally. By 1945, Japanese naval forces were reduced to kamikaze attacks because conventional tactics had proven futile against enemies whose technology made them nearly invulnerable to traditional naval combat methods. The Japanese Navy fought until the war's last day. Officers and men demonstrated courage, earning enemy respect. But courage couldn't bridge the technological chasm. The future had arrived on November 15, 1942, in Savo Island's darkness when Washington's radar locked onto Kirishima and demonstrated naval warfare had entered a new era. That future belonged to the nation that had built it, deployed it, and continuously improved it through systematic industrial effort, transforming laboratory advances into fleet-wide capabilities. The Americans hadn't just won the naval war, they had redefined what naval warfare meant. The technological transformation's completeness became evident in post-war analysis. American ships commissioned in 1944-45 operated with capabilities that would have seemed like science fiction in 1941. Radar had evolved from experimental equipment to integrated combat systems. Fire control computers could track multiple targets simultaneously. Proximity fuses made anti-aircraft warfare mathematically lethal. Combat information centers fused data into comprehensive tactical pictures. Meanwhile, Japanese ships still relied on visual spotting and manual calculation, technologies that belonged to a previous era. This disparity manifested most clearly in the war's final naval battles. During the Okinawa campaign, American radar-directed gunfire destroyed kamikaze aircraft with terrifying efficiency, while Japanese ships attempting similar defense achieved minimal results. The technological gap had become unbridgeable. Japanese commanders understood they were sending men on suicide missions not because they wanted to, but because they had no other options. Traditional tactics had become obsolete against enemies, who could see in darkness and shoot with machine precision. The industrial dimension proved equally decisive. American shipyards produced not just more ships, but better ships with each production cycle. The Essex-class carriers improved throughout the war, incorporating new radar systems, enhanced anti-aircraft batteries, and improved damage control. Japanese shipbuilding, hampered by material shortages and bombing raids, struggled to maintain existing capabilities, let alone introduce new technologies. The gap widened with every month of war. This technological industrial advantage created a strategic paradox. Japanese naval doctrine emphasized the decisive battle, where superior training and tactics would overcome numerical disadvantage. But American technology made the decisive battle impossible to win. Japanese forces couldn't get close enough to employ their advantages, while American forces could strike from beyond visual range with devastating effect. The very concept of naval combat had changed beneath their feet. The lessons resonated through post-war military development. American investment in research and development became permanent policy. The institutions that produced radar, the Radiation Laboratory, Naval Research Laboratory, and industrial partners, evolved into the military-industrial academic complex that would dominate Cold War defense planning. The systematic approach to technological warfare perfected against Japan would later produce nuclear weapons, jet aircraft, and guided missiles. For Japan, the defeat prompted profound reassessment. Officers like Amori and Okumiya spent their post-war careers analyzing what went wrong. Their writings helped shape Japan's post-war security policy, emphasizing technology and alliance over unilateral military power. The lesson that technological superiority could trump traditional military virtues became deeply embedded in Japanese strategic thinking. The human dimension shouldn't be forgotten. Kirishima's sailors fought bravely against impossible odds. American technological superiority didn't make Japanese courage irrelevant. It made it insufficient. This fundamental truth would echo through subsequent conflicts where technological gaps determined outcomes regardless of the combatant's relative will or skill. The Pacific War's naval campaign ultimately demonstrated that industrial warfare had evolved into technological warfare. Numbers still mattered, but technology mattered more. The side that could see first, shoot straightest, and integrate systems most effectively held decisive advantage. This lesson would define military competition for the remainder of the 20th century and beyond. In the final analysis, the United States won the Pacific Naval War because it built a better technological system, not just better ships. The integration of radar, computers, and communications created capabilities that exceeded the sum of their parts. Japanese forces, for all their courage and skill, were fighting a system they couldn't match and only partially understood until too late. The night Kirishima sank marked more than one battleship's loss. It marked the end of an era in naval warfare. The future belonged to those who could master the invisible battlefield of electronics and automation. That future had arrived, and its implications would shape global security for generations to come.